Morning, everyone. I'm Milind Pandit. I'm from the University of Cambridge, and I work around coupled resonators, dabble a bit with using nonlinearity to essentially help out, or working with nonlinearities rather than avoiding them. I just want to run you through some the roadmap, essentially. Today, we're going to talk about a bit of mode localization, a bit of background about it to those who are not familiar with it. Look at some of the modeling of nonlinear modeling of the coupled resonator systems, then look at the motivation for this research, and then I'll walk you through some of the experimental characterization, and finally discuss some of the results that we've seen. So in terms of mode localization, it was first brought to us from P.W. Anderson in '58 in the field of solid state physics. Since then, it's sort of moved on from solid state physics to solid mechanics, and now we're using it in MEMS. What is mode localization? Essentially, it's the confinement of vibration energy in a symmetrical system upon breaking that symmetry. It can be explained very easily with a simple 2-degree of freedom system with stiffness and mass values that are equal. So we've got two spring mass systems, similar K and M values, and that are coupled with a weak spring. Now, if we apply some sort of stiffness perturbation and change this symmetry, make it asymmetrical, we see that vibration energy gets localized to one of those, spatially localized to one of those systems. And this can be used greatly with respect to amplitude measurements instead of the traditional frequency shift measurements that we're all used to in the MEMS world. Just to give you, oh, maybe this is not going to work out, apparently. Oh, well. So I had an animation planned, which was working a while ago, but seems like changing of computers has made it not work. So essentially on the left, we've got two different modes that we work with in our labs. They're double-ended tuning fork systems. So they have two modes, the in-phase and the anti-phase mode. And you can see the weak mechanical coupling there. When we apply a perturbation, we see that in both the modes, we see that the vibration energy gets spatially confined to one or the other resonator. So this is just going on a bit more visual experience of what mode localization looks like. Coming to the spectrum, so we are going to be measuring amplitude ratios here. So how does amplitude ratio change with these perturbations that we're working with? So in the center, we have the symmetrical case where there's no perturbations, and the amplitude ratio is 1, which means the vibration amplitude of both the resonators we're working with are equal. On either sides, we've got the asymmetrical case where the vibration amplitude of one of the resonators is much larger than the other one. So there's been a lot of papers written about which operator region should we be working in. And a lot of people have been talking about working in the asymmetrical case, so higher amplitude ratios, essentially. And the reason behind this is one, that it increases sensitivity to stiffness perturbations, and second, we see that there's a linear shift with stiffness perturbations that we can make use of for sensor applications. What I'm going to be talking about in this research is working around the symmetrical case, essentially. And the reasons behind that is because we're dabbling a little bit with nonlinear vibrations and trying to push our system to the limits of the energy that it can hold in it. So we're going to be working along the symmetrical case, and or more known as the veering zone. This is the nonlinear model that we're using. We're using nonlinear stiffness on both the springs of the spring mass systems, and we're also using a nonlinear coupling. We are using an electrostatic coupling in this case. So unlike most mechanical systems, this is actually a negative coupling that is due to the capacitive plates that we're working with that are going to couple the systems. So we've got a simple system here. We are not thinking about nonlinear damping at this point, just to make things simple. Of course, that will be the next step when the time comes. So simulating the system in Simulink with a simple transfer function method, we see that we're working with two different drive amplitudes, which essentially correspond to two different operating regions. One in the linear, which corresponds to 25 millivolts here, and one in the nonlinear or beyond bifurcation, which corresponds to 125 millivolts. And as we can see here, in the veering zone, or where the system is matched and the stiffnesses are matched, in the symmetrical region, we see that the deviation from amplitude ratio, if we're thinking amplitude ratio as an output metric, the deviation of amplitude ratio with the drive amplitude is minimal. So we thought, what can we do with this? This is a very interesting phenomenon that we're seeing here. And this leads me to the motivation of this research, in that for a while we've been trying to work with amplitude ratio output metric to compare with the frequency shift output metric, which is so conventionally used. And one of the problems that we've been seeing is stability at lower integration times. And one way in which we can increase this low integration time stability is driving it at higher power so that we have a higher output signal. Now, our system is limited by electronic noise, and in such a case, having a higher output voltage will allow us to achieve better resolution, essentially. And that's where the motivation comes along, to try and equal the frequency shift method of sensing one way or the other. If we move on to the experimental section, so this is a micrograph of a couple of resonators that we're using. They're double-ended tuning forks, as we've talked about before. And in the middle, you can see that they're capacitively coupled. Oops, the other way around. So there's a capacitive coupling there, and that's weakly, and it's very weak, and that's very helpful for mode localized sensing, because that coupling essentially describes the sensitivity of a device. And the lower the coupling, the higher the sensitivity that we can achieve. And the setup essentially involves a closed loop approach. We're using two Zurich Instruments lock-in amplifiers, and they help us with both the readout, measuring the amplitudes, frequencies, as well as they have a very nice PID, PLL function that we can use to develop a self-sustaining loop, essentially. This is our PCB. We've integrated our MEMS chip into the PCB to reduce any parasitics and allow for better integration with the electronics. If we move on to the results, so the way we've designed this experiment is we've worked with three different operating regimes. One of them is in the linear regime, so a small amplitude of vibration. One of them is at nonlinear bifurcation limit, which is generally the limit before instability kicks in, and one beyond bifurcation, where we see the instability already in place. And as prescribed by our simulations, we see that around veering, which is around here, which is the symmetric case, amplitude ratio 1, we see the best insensitivity to drive power variations, or it seems as if the amplitude ratio remains constant across different operating regimes, essentially. And as we move away from that symmetrical case to higher amplitude ratios, we see that the amplitude ratios vary a lot more. This plot shows us about this as well. Around amplitude ratio of 1, we see that the fluctuations remain within 3% or so, as compared to away from that symmetrical case, where it could go as high as about 15%. So we wanted to understand more about why this is essentially happening, and this also is directly a reason why, from our drive and sense configuration, essentially, it's a byproduct of that. And we found the answer essentially in just open loop sweeps of frequency and amplitude curves. These are experimental results that we've achieved. So on the left, you can see a very small amplitude drive, and that has a very linear frequency response. And on the top, we see a matched response where amplitude ratio is 1, which means the vibration amplitudes are quite similar. And here we have one where the energy is localized to one of the resonators, and the amplitude ratio is a lot higher. Now, when we look at the nonlinear response of this, which means we're driving it at higher amplitudes, we see that in the matched case, the two resonators respond very proportionally to the drive amplitude and go above the theoretical bifurcation amplitude before we see that instability. However, when the amplitude ratio is greater than 1, far greater than 1, we see that although the theoretical bifurcation limit is here, we see that this little this resonator actually goes into an unstable regime, even though it's not vibrating at that vibration amplitude. And that results in a disproportionate change in the amplitude ratio, which results in this variation of amplitude ratio when we go from linear to bifurcation to beyond bifurcation regimes. So to conclude, we see that we've shown that there is amplitude ratio immunity around veering or around amplitude ratio of 1, which means when the resonators are matched, we see that the drive power variations to that affect the amplitude ratio are minimum. This working around this region could potentially allow us to have higher signal to noise ratio by pumping more energy into the resonators, and could potentially increase the resolution of the mode localized sensors. And finally, if we think of these variations as an exaggerated version of variations we see in an oscillator with the drive power, we can say that potentially this could also decrease this drive power variation noise. Essentially, that would be part of the amplitude ratio noise that we would also minimize. So has a lot of potential in terms of where we can take this, and dabbling around with the nonlinear dynamics of these coupled resonators could lead to very interesting results in amplitude measurements and amplitude ratio measurements. Thank you.